So I was saying that conditions for equilibrium should be the forces must come to zero. Remember, when we talk about forces, it's all forces. But if it is, say, an object, say, placed on a table, then we talk majorly of mechanical forces, because those are the forces that would make it move. Now, we also said that the torque, which is the distance from the pivot times the force, must be zero. Remember that torque is equal to R times F, where R is the distance and F is the force. So remember, the R and the F are perpendicular to each other. That is why when we take the sine of 90, then it is 1, and we get that. So the forces and the forces on this system and torque must be zero. Of course, torque we recall is the turning effect of force about a point. Now, on frictional forces, I remember, I maybe briefly, I left you to look at the difference between static and kinetic friction, and you are also supposed to look at rolling friction. But before we do much, maybe I can quickly say that some of the conditions for friction are these people joining when people started. Where were they? After 10, I'll not admit anyone. So let me admit exactly at 10 now, I'll not be admitting any other student. Where are they now? They have disappeared again. So we were saying that about friction, which generally is a force that tries to oppose relative motion between bodies in contact. We note that when an object is moving, friction and the perpendicular. Friction is perpendicular to the normal. Friction is perpendicular to the normal. Is it perpendicular? No, friction is proportional actually and perpendicular. It's not only perpendicular, but it's also proportional to the normal. We also note that friction is independent of area of contact. Friction is independent of area of contact so long as that area exists. Then we also note that coefficient of static friction is slightly greater than the coefficient of kinetic friction. That is, just before a body starts motion, the friction is higher than when it is already moving, That is the reason we are saying that coefficient of static friction is higher than the coefficient of that is the reason we are saying that coefficient of static friction is higher than the coefficient of kinetic friction. So we also note that friction depends on the nature of the surface. Friction depends on the nature of the surface. So far, we are 49 out of about 80. Some are coming in. I want to leave them out, but I'm again taken aback. So I take time to admit them so that we move on. So after noting all that, finally we say that friction depends on the nature of the surface in contact. Now, I don't know what you got about rolling friction. Can you, so far I have nothing to share because I'm just still giving a brief of what we have done before. Rolling friction, can somebody write something about it? Rolling, what is the difference between kinetic friction and rolling friction? Is there a difference? And what is the difference? I'm talking about difference. Kinetic and rolling, the difference. Between kinetic friction and rolling friction. So those are some of the things that we need to look at, or you need to look at for that matter. Now, I left also something to be on work. And when we talk about work, work is done when there's motion. Force is applied, of course, but you know, this of this body or change in position of the body is what brings us to, I mean, is what brings work. So work is the product of the component of force in the direction of motion. Work is the product of the component of force in the direction of motion. In the direction of motion, yes. And the direction through which the force acts. And the direction through which the force acts. So that is, work is equal to F cos theta dx. Where, remember, the x is the change in position. We are changing position from A to B. So, okay, if I may ask, is work a scalar or a vector quantity? Is work a scalar or a vector quantity? Is work a scalar or a vector quantity?
I think it's vector.
It's a
vector quantity.
Vector.
A vector quantity.
Someone is saying it's a vector quantity. Another one. Why is it a vector quantity? Why is work a vector quantity? Okay, when we look at work is force. Go ahead. Someone was talking.
The result of the product of a scalar and a vector.
So it's a someone is saying it's a scalar, someone is saying it's a vector. So now do I choose? It's a scalar. So can you maybe for our work today, can you check why it's a scalar or why it's a vector and give your reasons why it is either, or of course it cannot be both. I think it's a scalar. Now give us reasons why it is. So that will form the basis of our work. And maybe I may comment that as much as most of you did the work, but a few just copied from others. It was glaring, though we will not agree anyway. So it's not debatable, but I could see something else happened. So next time, of course, I won't allow that. For this, I wanted just to know the people I'm dealing with. But later, of course, it should not be allowed. Now, when we define energy, energy is ability to do work. Of course, that one we had done before, or capacity to do work for that matter. A system may have energy, that is kinetic energy, potential energy, and other forms of energy. We have several forms of energy, actually. We have mechanical, electrical, chemical. We know that energy, you cannot destroy energy, but you can always change or transform, actually, energy from one form to another. And that is the principle of conservation of energy. You cannot destroy energy, but you can always change. Like if we were to talk about maybe which one is the best now? When we change electrical to kinetic, what do we, if we change electrical, why? If we change, my pen is not picking. If we change electrical to kinetic energy, we use what we call what it is, electrical to kinetic. That is done through what? Electrical to kinetic. Kinetic to electrical. We can also do mechanical, just to mention a few, mechanical to electrical. Of course, we know that we need a device to transform energy, one form of energy to another. Like if we have kinetic and we want to change it or transform it to electrical, what do we use?
Transducer.
Of course, transducer is a general term used to convert one form of energy to another. But now, which specific transducer do we use? Kinetic to electrical. No one knows.
Dynamo.
Dynamo, I think so, because dynamo turns, that's the kinetic part of it. In the process of turning, we convert that motion to electrical energy. Electrical to kinetic. Electrical to kinetic, what do we use?
A motor.
Electrical to kinetic.
Motor, yes. I'm saying motors, yes. And which other one? Mechanical to electrical. Is it dynamo again? Mechanical to electrical. Yeah. We have all disappeared now. Mechanical to electrical, what do we use? No one knows. Then I left you also to work, to give the work energy relation theorem. Did you calculate and the formula came or it brought problems? Ilikuja, did it come? Did you calculate, I mean, did you come up with this formula here? That is work. Are you seeing the screen?
No.
Not there, okay. Okay, let me see. I was just asking if you did this. Work is equal to a half. This formula here, a half m into v square minus u square. Did you work on that? It is visible now, Cindy. Is the screen there?
Yes.
Yeah, did you work out that? Of course, when we look at this energy, the work, energy theorem, this one, work is equal to that. We are seeing that this is the same as just change in kinetic energy, because we are seeing that it's basically, you know, it's a half mv square, maybe the final kinetic energy, minus a half mu square. This is what I left you to look at. And you guys are saying you didn't do this. See, that is too bad. Did you work from of course, work is equal to, you know, force by distance, force, distance, or displacement for that matter, which is the same as ma for force and the distance. Did you do that? Then, of course, for from here you go like ma into ma into distance. Of course, from those two laws we can say ut minus or plus, for that matter, a half gt square, like this. That is, of course, that is work is equal to that, which if you substitute and do a few things, you will see this will take us a long time. We'll see if you substitute for I mean, if you let me to move this. If we from this from S is equal to okay. Of course, that is S is what we have there. So let me not repeat that. From that, we can also see that from this formula here that V is equal to U plus 80, of course. If you substitute for this, and also remember that this formula here, V squared is equal to, that is the third law there, is U squared plus 2AT. So if we substitute that up there, then, or if we take a different color there for that, if we substitute that there, or if we substitute it back there, then we are going to have roughly, I think this one you ought to have done earlier on your own. You'll have something like a half. No, that one is not visible. You will have something like M into U V minus U square over A. This is this one here plus a half. I may interchange A and G, but they are the same thing, so please don't. Into again, into again, how did I do that? I think V square minus UV minus UV plus U square, something like that. U square, unless I've missed something. So something like that, where I want to move. How do I move with this? So with that, we can come back here. We can come back here. So that we have, if you go on and on, we'll have somewhere that's, you know, M into a half V square. I've jumped a few steps, minus a half V square minus a half U square plus UV, like that. That will be equal to work. So that finally you will have you'll have mem into V square minus U square plus 2 UV, like that, which now finally, of course, should give you what you need. So you will work that at home, or there's a way I did it that is different from what you may. Okay, this, whatever we have done here, you can follow from the handout, but there is also a way. Let me show you this other way. We can go this way. Let me just admit, I saw someone hanging here knocking. Oh, this one. So I was saying the same thing, we can go and do it this way. Let me have a new board again. The same thing, we can go this way. The same thing, we can go start and move this way. So the roots we have several routes. So apart from what we may have in the book, but what we have just tried to go through, we can use this. From F, of course, work is, of course, F times S or D, which will be the same as M A D. Then from this, from V square is equal to what? U square plus 2AS. So from this, can you make A the subject, then you substitute back here. Make A the subject in this, make A the subject here, make A the subject here in this. Then you substitute up here. You substitute it up there. So from there, you should get something. Is there anything coming? Oh, correction 2S. No problem with that. I've seen that. Yeah, V squared is equal. Yeah, of course. Yeah, you're right. V squared, yeah, it's 2S or Unisawa. There is no problem with that. Plus 2S, yeah. 2S Nisawa. That is what I wrote. V squared is equal to U squared plus 2S, yes. So from that, make A the subject, then move on. Are you getting any closer to what I'm imagining?
Yes, sir.
Yeah, so I think this one is easier because in the other one, there's something there that, remember, look at this. Let me just take you back to that. So of course, this is easier or more straightforward, but there's something there maybe that may bring problems. I don't know. This expression here, because remember, before I came to this expression here, before I came to this expression, is it this one? Okay. Before I came to this, just up here. By the way, why was this guy trying to correct this? Why? What was this guy saying that I could not see this one? Is this the 2S you are trying to correct? This one, I don't know. But this is okay. So anyway, what I wanted to say is that before we come to this last step, this one, before we came to this, before we came to this, this one here, you are seeing just that step. See, we went this way, or you are supposed to go this way. This one, if you multiply here, then we'll have, so we will only, once we have multiplied by that, we are going just to use the is it called the denominator or numerator, the upper one, E to this upper 2, E, this one will reserve, so that we will bring it out and we have M over 2 into now, V square. Actually, that is how we came to this, that is how we came to the second step. Now we take the 2 out and all that, so that, eventually this 2 is here. I think I forgot to write that. So that 2 is there. So that's how this came. Maybe for some, you cannot see how this came about. So that's what I'm talking about. So that's okay. So you choose whichever path. So what does the theorem say? The work energy theorem. It states that the net work, that is the work energy relation of the work energy theorem states that the net work on a system, the net work on a system is equal to the change in kinetic energy. The net work on a system is the same as the change in kinetic energy. That is why we have, that's why we have U square, V squared minus U squared. That is initial and final. Of course, going to power, I don't think we can talk much about that. Power, of course, is the rate of how to manage your work. So what I can comment about the power is this relation here. We know that, power the same as the rates of doing work. That is, we have the time. That's the rate of doing work. That is the same as, force, that is for work, force times distance over time. So if we take the rate of change, if we take this, if we take say, if we take the rate of this, the rate of change of this, that is the delta here, the rate of change of that, then we can say that this is the same as rate of change, if force is constant, the rate of change of distance, d or s for that matter, with time, which we can as well put this way. So this here, this here, E, is the same as change in velocity. So is the same as velocity. So we can say that this is the same as that. So we can say that power can also be written as force times velocity. From that expression there, I think it's clear and there should be nothing about it. Of course, if we have rate of change in work, then we expect this as well. So that's where we are. Of course, from this, we also remember that we have IR. If we use electricity, is it I squared R, which is also the same as VI. So we note that. So all that gives us power. But of course, I'll give some little work about that. But now, let us do something else. I hope all this is clear. Somebody to help me state the kinetic theory. Now, who is this somebody? Can someone write it for you? We say that the work is the same as, work done on a system is the same as the rates of change of kinetic energy. That is the net work done on a system. The net, that is the kinetic, it is, it's called the work energy theory or theorem. But kinetic theory, of course, if that is something else. Now, basically here we are relating work and energy. So that's why it's called work energy relation theorem or the work energy theorem. Work energy theorem or work relation, which says that the network on a system equals the change in kinetic energy. Okay, now I was just about to talk about something else. So let to toy. I think I just need a new one instead of going that. Yeah. So let us look about rigid body. Rigid body or bodies. Fine. So when we say somebody is rigid, it means what? Someone is rigid. Can we get 2-3 messages in terms of response? When somebody is rigid in normal life, someone rigid means what? Can you type something? I see the message. When someone is rigid, it means what? Somebody, no, not moving. When someone is not moving, we say he is rigid or she is rigid. When you ask for, a friendship and someone says no, you say he's rigid. Or when somebody has said we go this way, then this person does not change. We say this person is rigid. He or she has a definite shape. Hardened, irregular. Irregular in shape means you are rigid, strong, serious, unyielding, static, can't. Imetosha, yawa, imetosha. So, okay. So when we talk about something that is rigid, it means it maintains the shape. It maintains the shape. That is the distance between the bodies within this system. Within this system remains the same. It does not change. So it remains the same. So we say that a rigid body is when the distance between 2 points of a rigid body remains constant, regardless of external forces on it. When the distance between 2 points on a body, when the distance between 2 points on a body remains constant, regardless of external forces. Whatever you do to this person or this thing, it will remain the way it is. Then this person or this system or this object is said to be rigid. Remember, we want to, see how this rigid body rotates about some point, We want to see how this rigid body rotates about a point. So to start us off on this, our body, let us recall that, remember we talked about this. L is equal to R times P. That is angular momentum of a body is the same as the R times P, which is the same as, of course, R times mv. That is, P is, of course, mv. So when we have a system like that, and we talk about, its rigidity, then remember, we are also talking about this. This system is made up of several, several particles, say n particles. So when we talk about the angular momentum, angular velocity or angular motion of this body, then we talk about the sum of, the sum of, these particles that make up the body. They are I particles times the velocity of this particle I. So we are talking of a body. You are made up of several particles within you. But now when we take each particle and we identify some point of rotation, then the sum of the momentum will be given by MRI times VI. Remember, you told me you were doing, what is it called? Pure math. Or did you say pure mathematics or what? Pure, or what did you say? Can someone remind me? Let me just check. Did you say you are doing pure math or what? What the lesson you had before this was called what? Yes, is what Bwana Moses. Okay, some maths anyway. What pure? Yes. So we have, of course, different types of maths. So when the tail of this thing is too long, what has happened to it? This tail is too long. Yes. So okay, this pure anyway. We know it. I hope you have talked about commutativity. Commutativity. Maybe let me hope. Okay, commutative. That is when we have something like this, for example, when we have F, not force in this case, just an arbitrary thing, F is equal to, say, A times B times, say, okay, even that. We can always also write this as F can also be equal to B times A. That is, you can multiply them interchangeably and still get the same answer. So that is basically what we have used here. So MRI times V, times that is L is equal to that. But now remember, we are talking about that system where made up of several particles which are rigid, they are not moving. So that is why we maintain R and RV. So what we're talking about is we are summing, of course, from I, that's the ith particle, to the nth particle. That is the last particle. So that is I will have value of 1 all the way to n. Is there, when I was doing biology a long time ago, I remember there was something that was made only of one cell or what? Can you remind me, those who scored A in biology? I remember there's a creature or something that has only one cell. What is it called? Those who did biology. A creature made of only one cell, it was called what? Or we have forgotten all that?
Amoeba.
Amoeba, yes. You are good people. So amoeba is monocell. So like in this case, if I is 1, we have that. But of course, if we have more, then the particles will multiply. So with that, we want this system now to rotate about a point. So let us define this. We want to look at this system as rotating about a point. So we talk about moment of inertia of this system, where now the moment of inertia of this system I will be given by m r square. Or we can say that this, we can put the subscripts I, depending on that is the moment of inertia of those particles. But remember, we have to, talk about a few things on this. Of course, here also, if the particle is made up of several, if the system is made up of several particles, then we still talk about I to be equal to n. But let us quickly go back and look at a few things. What did I want to tell you? Well, let us go back and look at this, or rather recall. We are talking about, let us talk about this system here. It is the, we are moving about a point. So still we are on circular motion here, basically. So we have this body. This is the x-axis, the y, and this body here is moving about some angle here. This is angle theta here. We have r, radius of the circle through which it is moving. Of course, after some time, if it is moving like that, we'll be talking about s, that is some angular displacement. And remember, we also have velocity of this body at a given point, which is tangential, that is v. So we have velocity there. This is an arrow here, and this is s, that is the movement along the arc, just a slight movement. Then we have the theta for the angle, and we have r is the radius. So we can say that if we consider maybe the x movement, we can say the velocity, or rather we can say that tangential velocity, that is vt, tangential velocity, will be given by the s over, this is s, the s over dt. And we can as well say that, remember, or rather recall where we said that, okay, let me write it, you will see where it, we will recall this hopefully. We can say that this is the same as the r theta over dt. Is that okay? Or people have disappeared? Anything making sense out of that? Ni sawa?
No.
What is not sour now? When we were talking about, were you there when you talked about the sine theta over s over r? Were you there when you talked about this? In circular motion, or yeah, in circular motion, yes. And we went ahead and said that as theta approaches, this is for approaches, that is a lot in pure maths, as theta approaches 0, comma, sine theta will approach theta. Hiyo uliona kweli? This my line is misbehaving. Oh. Sine theta is approaching theta, so that we can write that we can just write theta is equal to, that is for a very small theta, is equal to what? Is equal to s over r here. S over r. So that s, of course, it follows that s is equal to r theta or theta r, whatever. Evil. Is it okay now? So that is what we have used here. That is what we have used here. Iko sawa? Hey, no one is talking. Okay, sawa. So that is how we got to that. So we can go ahead with what we were doing from here. We can see that this here, we can see that, you know, we can see now that this, we can see now that this can be written as, what? As, of course, we can write that as Vt to be equal to r d theta over dt. evil, which from also what we did earlier, this one here, D, E, what is this? Yeah, can you recall that? Oi, mama yu ngumu. Can you, iko sawa? At least somebody has said iko sawa. So this is the same as now we can write this as, this one we can now write as R omega, you know. So basically we are saying that V is the same as R omega. I hope tuko sawa. So basically that is, we can also say, we can also from this then say that, we can also say that, what? We can say that acceleration also, AT, can also then be given as what? As R R D squared theta over D T square. Hapo ni sawa? Now Kivuva, unalia or you have gotten something? I don't know. No means what, Mercy? What are we deriving, sir? We are deriving acceleration. This one, this is 80. Maybe I didn't write it properly. A, this is 80. This is A. This is acceleration, A. AT, acceleration. That is why we have come with this. R D square theta over DT square. Are you okay now? Yeah, are you convinced or you are still suffering? If so anyway, so that is where we are. That is, you can see now that we can simply write this to be equal to this. We can now write to be equal to this is too close. Let me, how now? Do I rub or do I go to the next? Let me just go to the next one. Okay, we can now write, if I'm not wrong, we can write AT, that is acceleration anyway, to be equal to, this is what we wrote, is equal to, RD square theta over DT square. This we can just write simply as, we can write this as just, R is R alpha. Of course, alpha now, needless to say, would be, this is alpha, in your alpha, sasa. That's what alpha is. So that we can authoritatively actually say that F, if we go back to force, is equal to MA. can simply just be written as F is equal to M R alpha. So so we can say that is that. Of course, this is the same as you know, we can say that you know, we are seeing that this here we can say that we can say that we can also write tau, which was RF, if you recall, RF. We can write to be equal to I alpha. You can check on that. If there's something missing, let me know. So we can say that tau is equal to that from what we have done. If there's a problem, of course, let me know. So that basically, when we talk about a rigid body, then basically we can say that you know, we can say that for a rigid body, remember we had said that I is given by you know, I is given by what? M I R I R squared I. So that for a rigid body, I mean for a continuous body, we can say that this is the same as you know, the integral of M R I, which we can simply just write as you know, R square A, which we can simply write as you know, that is now when it's a continuous body, we talk about di, not just I, but we talk about di. So so our di here, for a di then we can now work on that and see. So that's where we are. So that implies that for a continuous mass, then we can simply write this to be R squared into M, rather into dm. If it's a sum of masses, then you can just write as you know, as this dm. Yeah, so I think that's where we are. I know there are a few stars here and there. But we can still look at that later and see what we have. So let us finally look at this, the law of conservation of angular momentum. The law of conservation of angular momentum. Remember, we had said that this is equal to RP. RP, rather, is equal to R times P, like that. We had seen that. So remember also we said that torque, this one, torque is the same as R times P, like that. So if we integrate angular momentum dt, and from the maths we have just talked about, this, as we are saying that it is d into r times p. Of course, here we have dt down here, and we close that. This is the same as, of course, Have you done what's called what? Have you done? Is it called differentiation by parts? This one. Have you done this? Differentiation by parts. Have you done this? Have you done that? Are you still there? Hello? Hello? Are we there?
Yes.
Oh, bwana. Sasa mmenyamaza, nimeshindwa. I'm talking to a ghost or ghosts or okay, someone is saying you have not. Oh, hey, Kivuva, your zeros are too much. No, it's just NO. Wait, Charlo. Anyway, so what I'm saying is, we can write this now as D R over dt times P plus dP over dt times R. So basically what we are saying is that at any given time we keep one constant and we work on another. That is basically what we are talking about. So what we are saying is that we can now say actually that we are talking about this is the same as V times P plus this is the same as what now? We can say this is the same as R times F. Is it okay? This is V. That is dr over dt is V times P plus R times F. Are you getting what we are talking about? Is this okay? Is this okay? Okay, I'm seeing someone at least, or is it me who has said okay? Oh, no one is saying okay on this. Okay, I've said okay. So this is the same as 0. That is V times P is equal to 0 plus R times F. Why is this 0? Why is this 0? Why is this 0? Why is this 0? It is because the V's are in the same direction. If you multiply two vectors in the same direction, you get 0. That's why we come to that. So we're saying that the L, or L for that matter, is just equal to R times F. And if you recall, this is the same as torque. Anyone suffering? dP over, okay, I'm getting that. Does it mean dP over dt is equal to F? Let me take you back. Oh, but we have an R here. Why are you talking? Okay, yes, you are right, yes. dP over dt. Remember, or rather recall, not remember. Recall that P is equal to M V. So that dP is the same as M dV, which is the same as MA. But what is MA? Which is the same as force. Is it okay now? This Ndubi, Regan, and what, Kirubi. Pole sana, but you can get some clue from Kivuva or who. Let me see his name. So anyway, you can see how we are going to that. How F changes to that. So basically, write this. Okay, basically what we are saying is that we are summarizing by saying that dl over dt is the same as tau, that is tau, which is the same as that stock, which is the same as which is the same as the summation, which is the same as the summation of Ri times Fi. So we are saying that the rate, or rather we are saying that the net torque causes the particles angular momentum to change. We are saying that the net torque causes the particles angular momentum to change. Or put differently, we can say that the rate of change of the system's angular momentum, the rate of change of L, the rate of change of the system's angular momentum is the net force on the system. So I think we stop at that. Try to look at the equation. In case of anything, try to look at this together with the notes. In case of problem, let me know. It's A.
Excuse me, sir.
Yes.
Okay, thank you for the lesson.
Yes.
But I think there's something we may have skipped. The last time we had the lesson, the last thing we did was introduce friction. We only stated the 3 types of friction.
Yes.
Yeah, and that was literally the last thing. So I think we need to look at friction.
But when we came today, did we start by overall looking at what friction is and the conditions? Were you there?
Yeah, yes, I was.
So we started by looking at the conditions of friction and types of friction. Did we do that?
Yes.
I also left you to look at rolling friction. So what else, Madam?
Maybe doing some examples.
Example, did I give some work on friction?
Yes.
Which you handed in?
Yes.
Yeah, so the rest you do on your own, unless I give more problems, which I can do later.
Okay, thank you.
But all this you do together with the notes. You read, because mostly if you check, you may realize that a good percentage of my time I don't go through the notes, but somehow when you read them side by side, then you realize maybe I've come up with a better way or a cheaper way, or so you go through and check which one do you take. Do you take mine? Do you take the one in the notes? Because notes is a guide, Anybody with a question again? You are welcome. No one is talking again. Do I assume everything is fine? So please check at the mathematics. I know it's a problem, but still we can slowly go back and check where you are floating so that we make things work. Assignment I cannot go through because most of you got 5. So unless you cheated, it should not be a problem. Yeah, you are reminding me. There are those people who did it late. Going through notes is not a crime, but I've just said you try to go through the sketch I'm giving plus the notes. It will be clearer, if you combine the two. I'm not saying you abandon the notes. No, go through my work, go through the notes, then you get somewhere to fall. Someone is saying, hey, I have to rush somewhere. Please let us stop at that and we talk later. I'm seeing questions coming, but I'll give you a session maybe later. Yes.
Thank you.
I'll give you a session later, maybe whichever day, but not now. Now you'll spare me. I have to rush and be in another meeting.
Okay.
But try to check these things in case you are stuck. We can start from there. We can revise poly as we move. And also remember to check the R's. My R's and the V's, they appear to be almost the same. So you read my lips as we also, as I write, Hey, Sawa. You go to church or mosque, tomorrow and weekend. Don't just hang around. Church, mosque, whichever, whichever religion, please go to church. Aya. Those who didn't hand in their assignment in time, of course, that is a 0.
Wow. Hivyo ndo ana life.